Hello friends, once again welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 7 equilibrium, and in this video we will discuss about Brönsted Lowry acids and bases and Lewis acids and bases. First come to the Brönsted Lowry acids and bases. According to Brönsted Lowry theory, acid is a substance that capable of donating a hydrogen ion H plus, and bases are substances capable of accepting a hydrogen ion. In short, we can say acids are proton donors and bases are proton acceptors. See this reaction. This NH3 plus H2O converting into NH4 plus OH minus. This NH3 is converting into NH4 plus by adding proton. Okay, and addition of proton, that is a base. That's why we can say NH3 is base. And this H2O, this is converting into OH minus ion by losing proton. So we can say this H2O is acid. Okay. So in this reaction, water molecule acts as proton donor and ammonia molecule acts as proton acceptor and are thus called Lowry-Brönsted acids and base respectively. Okay. If we consider the reverse reaction, then this NH4 plus is converting into NH3. That is, it donates the proton. So NH4 plus is acid. And OH minus ion is converting into the H2O by accepting proton. That's why this is base. Okay. In the reverse reaction, H plus is transferred from NH4 plus to OH minus. In this case, NH4 plus acts as a Brönsted acid while OH minus ion acts as a Brönsted base. Okay. Now, if we consider this one pair, that is this NH3 and NH4 plus, this is a one pair of acid and base. In the same way, this H2O and OH minus ion, this is again make one pair of acid and base, and this pair differ only by one proton. Okay, that's why such type of pair is known as conjugate acid base pair. The acid base pair that differs only by one proton is called a conjugate acid base pair. Okay, again if we consider this reaction, NH3 plus H2O converting into NH4 plus OH minus ion. OH minus ion is called the conjugate base of an acid H2O, and NH4 plus is called conjugate acid of the base NH3. If Brönsted acid is a strong acid, then its conjugate base is a weak base and vice versa. Ionization of hydrochloric acid in water, consider this. In this case, HCl acts as an acid by donating a proton to H2O molecule, which acts as a base by accepting a proton. This is HCl. This is converting into this Cl minus ion by donating proton. That's why this is acid, and this Cl minus, this is its conjugate base. So we can say this is HCl and Cl minus make conjugate acid base pair. The same way, this H2O add proton and converting into H3O plus. This is adding, this adds the proton. That's why this is base and its conjugate acid is H3O plus. Okay. Now, dual role of water as an acid and a base. In case of reaction with HCl, water acts as a base, while in case of ammonia, it acts as an acid by donating a proton. So we can say water is amphoteric in nature. These two equations can be represented. In this case, this H2O is converting into H3O plus by accepting proton. That's why in this reaction this is base, while in this case this H2O is converting into OH minus ion by losing proton. That's why this is acid. Okay. Now there is one question, problem 7.12. What will be the conjugate bases for the following Brönsted acids? HF, H2SO4, and HCO3. These are the Bronsted acids, and we have to find out their conjugate bases. Okay, so we can say what are Bronsted acids? Bronsted acids lose the proton, okay, and make conjugate base. So simply we can say the conjugate bases should have one proton less. Okay, so HF is a Bronsted acid, and its conjugate basis, when it loses the proton, it will form F. And when it lost the proton, it acquired the one negative charge. That's why this is F minus. The same way, this is H2SO4. By losing proton, this will convert into HSO4 minus, and it gain one negative charge. This is HCO3 minus. When it lost this proton, it will convert into CO3, and now it has two negative charge. Okay. Write the conjugate acids for the following Bronsted bases: NH2 minus, NH3, and HCOO minus. Now these are Bronsted bases. It means they accept the proton and convert into conjugate acids. So we can say conjugate acid should have one extra proton. Now in H2 minus, if we add the proton, that is H plus, and this is NH2 minus, we will get the neutral species NH3, which is its conjugate acid. NH3, which is already neutral, when proton is added to this, we will get the NH4 plus. HCO minus, when proton is added, this will convert into HCOOH. Next, problem 7.14. The species H2O, HCO3 minus, HSO4 minus, and NH3 can act both as Bronsted acids and bases. For each case, give the corresponding conjugate acid and conjugate base. See, its solution is, these are the species. Okay. Now, first we will find out its conjugate acid. It means we are assuming that these are conjugate base, and conjugate base means they accept the proton. So H2O accept the proton and convert into H3O plus. HCO3 minus accept the proton, convert into H2CO3. Be careful when you write the charge. This is neutral. When proton is added, this will convert into positively charged H3O plus. This is already one negative charge is there. When proton is added, we will get the neutral species H2CO3. HSO4 minus, this is negatively charged. When proton is added to this, we will get the H2SO4. NH3, this is a neutral species. When proton is added, we will get positively charged NH4 plus. Okay. Now to find out the conjugate base, now assume these are the acids. These are the acids, and acids are the proton donor. So after donating proton, H2O will convert into OH minus. HCO3 minus, after donating proton, convert into CO3 2 minus. Okay. HSO4 minus, after donating proton, convert into SO4 2 minus. And NH3, after donating proton, convert into NH2 minus. In this way, we can find out conjugate acid and conjugate base for the same species. Lewis acids and bases. According to this, acid is a species which accepts electron pair. Base is a species which donates an electron pair. Okay, for example, BF3 is an acid. Okay, actually, in case of BF3, the octet of this boron is not completed. Okay, boron has only 6 electrons in case of this BF3. So it is an electron deficient species, and it can accept electron. And when it reacts with the NH3, and we know in case of NH3, nitrogen has one lone pair of electron. So this lone pair of electron can be donated to the boron of BF3. Okay, so BF3 is an acid and reacts with NH3 by accepting its lone pair of electrons, and this reaction can be represented like this. BF3 plus NH3, this lone pair of electron is donated to this species. Okay. Electron deficient species like AlCl3, CO3 plus, Mg2 plus, etc. can act as Lewis acids. while species like H2O, NH3, OH minus, etc., which can donate a pair of electrons, can act as a Lewis bases. Okay, now in these Lewis bases, this H2O and NH3, these have the lone pair of electrons, and this OH minus ion, it also having the one extra pair of electron which can be donated. Okay, in simple way we can say generally positively charged species are Lewis acids, or electron deficient species are Lewis acids, and negatively charged species or neutral species having lone pair of electrons act as Lewis bases. Okay, see one problem 7.15. Classify the following species into Lewis acids and Lewis bases and show how these act as such. Okay, HO minus, F minus, H plus, BCl3. We have to classify at the same time. We also give the reason. Now OH minus ion. This hydroxyl ion is a Lewis base as it can donate an electron pair. Fluoride ion acts as Lewis base as it can donate any one of its 4 electron lone pairs. A proton, this H plus, is a Lewis acid as it can accept a lone pair of electron from bases like hydroxyl ion and fluoride ion. BCl3 act as a Lewis acid as it is electron deficient. It can accept a lone pair of electrons from species like ammonia or amine molecules. Okay, thank you.